So, welcome again to the V4Safety webinar on simulation structure and the V4Safety processor. And this is I think, the fourth webinar that we have in this series for the V4Safety project, which is running to the end of this month. So it's a 3-year project and almost finished. So we have results to show to you. If we look at the presenters today, my name is Sietse Kalesvaart. I'm a project manager at TNO in the Netherlands, and also the coordinator of V4Safety. And our second speaker, Peter Wimmer, is, we have an announcement. He is ill today, and Lars Schoris has offered to take over his role. So will do most of the presentation. Peter Wimmer is at Virtual Vehicle Research Center. He is also work package leader for the work package in V4Safety on simulation structure. And so he's been very active. He is also let's say the originator of the V4Safety processor, which is an interactive tool. We will talk about that later. The demonstration of the V4Safety processor will not take place in this webinar. We will explain the principles, and then later we will record the demonstration and send you a link where you can find the recording of using the processor, and it will get online as well. So our main speaker is Lars Schoris, and Lars, maybe you can quickly introduce yourself.
Yes, sure. Hi, everyone. My name is Lars. I'm responsible for our simulation department at ZF, ZF Engineering Solutions, what we call ourselves. And I'm working together with Peter and Sietse on the V4Safety project and also in the P.E.A.R.S initiative for quite a while. And I'm happy to share some results of our, let's say, work over the last 3 years to you today.
Yeah, thanks for taking over, Lars. That's very convenient. So I will introduce in a couple of slides the project, and then we will quickly go to this simulation structure and the model selection. Good. V4Safety is all about accidents. So how can we avoid them? How to prove that the safety measures that we take are actually better? And what do we compare to? So what is the original situation that we want our improved system to compare to? Those are some key questions for V4Safety. It's a Horizon Europe project ending this month. There's a very strong role for vulnerable road users. So how, from a vehicle perspective, can we help to reduce the number of accidents and the severe accidents with vulnerable road users? So we're talking cyclists, e-scooters, pedestrians, etc. Motorcycles as well. We look in V4Safety at prospective safety assessment. So if I introduce this safety measure, how much safer would it be? Always looking ahead. Our purpose is to build a transparent framework based on simulation, so that studies with simulation become more comparable. We look at safety measures that can be in vehicle, like an improved AEB for cyclists, for example, or changes in infrastructure, like changing the layout of a zebra crossing, or policy, like changing speeds or changing the regulation for driving permits, for example. And in the end, our main goal is increase the reliability and the acceptance of simulation as proof for prospective safety assessment, and maybe in the future also proof for type approval. Good. So our objectives are a framework for predictive assessment. Then how to use behavior models in this, so human models, for example, but also automated driving models. Then a methodology for baselines, so the original situation and the original accident data that we want to compare to. Then how to properly use models of safety measures. That's very much the topic of today. Demonstration with use cases. So we did over 10 use cases and testing the framework and the simulation structure. And a methodology for projection over time and across regions. So you might imagine a study is dealing with accidents in, say, the Netherlands. What does that mean for Belgium or France? And what would that mean for a study or for the road situation in 5 years from now? So Lars already mentioned the P.E.A.R.S network. This is a network that a volunteer network that works on prospective safety assessment and using simulation. And it also feeds the V4SAFETY results into this ISO working group. Good. If we talk about the partners, then there's 17 of this of us. It's a sizable consortium, but that actually makes it very effective. And if we talk about today, then first of all, we talk about simulation scope. This is the image of the V4SAFETY framework, which has 3 phases: preparing the assessment, executing a simulation, and analyzing the assessment. In a way, the simulation structure is very central to in the middle, but actually is defined here in the select models stage. So that's mostly what we will talk about, and it sets your configuration for your simulation. So I just want to let you know there's more webinars coming up. So tomorrow there is one on projection and extrapolation, and there is one Thursday on human models. So on our website you can find the registration and the details of these webinars. Much recommended. So this is where I will hand over to Lars. Before that, a couple of things on the way of working. So there's a Q&A button, should be in your screen somewhere, where you can raise questions. You can raise them ahead, and we will save them until the Q&A part in the presentation. There's also a chat box. Q&A is preferred, but if you can't find it, you're also allowed to use the chat box. So here I hand over to Lars and enjoy the session.
Thank you, Zitze. Yes, hello everyone again from my side. I will take over the parts of Peter, so I'm sorry, I do not definitely have the correct wording as maybe Peter would have, but I'm trying to do my best in this session. Yeah, so what it's about, introduction to model selection. As Zitze just said, it's part of the overall V4SAFETY framework. And yeah, in the work package number 5, we really thought about how to select models and try to document all this into our deliverable 5.1, which will be soonish available to everyone. So it's about select models, and select models cannot just be by itself. It also has to have a connection to the different assessment topics. On the one hand, there is the evaluation scope. So if you have attended the other frameworks, you always start with the evaluation scope, basically what you want to do. You want to assess the safety measure, you want to maybe address some road users, you want to know what you really want to assess, what is the metric. So this, of course, has influence to the select models part. Then, of course, there's the so-called, how to compare to or what to compare to, the baseline approach, so the reference set, which influences as well the select model approach. And then finally, the prepare data. So what kind of models are available, what parameters I need also has influence to select models. And then there's an interconnection to the configure simulation. The simulation structure, the modeling approaches we have chosen need to be configured together that it can be simulated in an overall, let's say, simulation toolchain co-simulation part. So what questions want we to answer today? For example, what simulation structure is required to generate results that meet the given evaluation scope? Which elements should be at least consist of? So it can be, of course, very extensive, but we also thought about, okay, what is the minimalistic, the required set you need to have for models? What are suitable modeling approaches for each of the elements in the simulation structure? And how should the models be connected during runtime and to initial boundary conditions? When we talk about an overview, how to process the topic of choosing the right models, we always start from the evaluation scope I just stated. The select baseline approach, so the baseline we need to have defines the simulation structure in a way. And here we need to think about what is the simulation structure maybe. Then based on the simulation structure, we go to the select modeling approaches for the pre-crash simulation elements. So all elements which are in a way before the crash happened. And then we need to think about models maybe for the in-crash simulation as well. And we need to think about model interfaces. And finally, we come to the simulation structure and the modeling information, which is then needed for the configure simulation part. So what would be a very generic simulation structure from our point of view? We have on the one hand side the pre-crash elements, which are consisting of like traffic elements, infrastructure elements, but also environmental elements, weather, lighting, day, night, whatever conditions. In-crash elements are in a way risk curves, finite element simulation models, collision consequences. All this has been connected with the simulation control, and this can be changed then or influenced by different kind of regulations. So if we want to think about performance assessments, we have influences maybe from policy, regulation, and stakeholders. There can be different kind of measures we can define, so legislation can define in-vehicle safety measures, which will influence pre-crash elements of the simulation structure, but also in-crash elements. Infrastructural safety measures can be defined, which will also influence the risk, maybe the in-crash parts, but also, for example, infrastructure designs. And finally, we can think about behavioral changes, which will mainly involve traffic participants. So how do they maybe change their behavior? And then we can compare before and after to perform our performance assessment. So the defined simulation structure, how do we go with that? The first thing, as said, the evaluation scope. We have the safety measure type, the addressed road user. We need to select suitable simulation structures. And since we have quite a holistic point of view from the V4Safety and not just focus on in-vehicle safety measures, we have a bunch of so-called simulation clusters which can be used or can be used for the model selection approach. We have on the top, we have in a way the road user to be protected. Can be pedestrians, scooters, cyclists, power two-wheelers, passenger cars, commercial vehicles, but also ego vehicle occupants. And we have on the other hand the safety measure or the technology we want to assess can have different kind of implications. So it can be an in-vehicle pre-crash safety measure, like an AEB system, for example. It can be infrastructure-related pre-crash systems, speed bumps, changing the velocity of a car. It can be something like behavioral changes of the ego, so the occupant or the driver of a car, for example. It can be behavioral changes of other opponents. And it can also, of course, be in-crash related measures, changing the restraint system, changing in a way structural elements on an infrastructure that reduces the injury outcome finally. So overall, we see 42 different combinations which are possible to create a simulation structure. And to reduce the complexity a little, we thought about, okay, maybe there are clusters available, and these clusters can be seen here. So overall, we have 15 different clusters which can be used to define the correct simulation structure. And how this looks like, we will see in the next slide. Very basically, the simulation structure details we divide on the left-hand side between pre-crash elements. So there's a pre-crash cluster here, or the elements. We have traffic participants, with have mechanics part, human parts, technology parts. The opponent, mechanics, human, and technology, so quite similar. Then there's infrastructure elements, a road signs, surroundings, temporal modifications, and of course also environmental conditions, weather, lighting conditions, traffic license states, V2X communication maybe as well. Then there is the simulation control part, which is always, you see it here on the legend point of view, necessary elements, avoidance detection, collision detection, input generation. And the in-crash part as well defines an own cluster point. So we have in-crash simulation models, which differ from each other based on the applied metric. So we can have different kind of metrics. You see it at the way later as well. Safety criticality and crash parameters, in-crash kinematics, VRU, injury assessment. So based on the metric you choose, you have to do different kind of simulations to perform those assessments. And if you choose the different clusters, okay, one more time. So this is the safety technology which will be assessed. This is of course mandatory. The mandatory elements, this is the minimum requirements we see for the different clusters to be used. And then optional parts. So maybe you want to assess as well lighting conditions, but you normally do not have to use such things. Very shortly about pre-crash or in-crash related safety measures. So when you think about when do I need really in-crash related safety measures, on the left-hand side, we have here the cluster number 9, in-vehicle in-crash measure. So if you want to, for example, change the restraint system, you need to have mechanics, ego, opponent, the road definition, and you need to think about your ego vehicle information to really talk about in-crash safety measures. So this is what you need. And then the technology is also applied here. So finally, you need to perform as well in-crash simulations to assess your technology. When you talk about pre-crash related safety measures, for example, here in the cluster number 7, it's about the behavioral changes from the opponent. The technology lies in a way here in the opponent human part, and you do not necessarily have to perform in-crash simulations as well. Maybe it's sufficient to assess pre-crash related safety metrics. Okay, so if the safety measure is pre-crash related, you have to perform step number 2, metric category dependent definition of in-crash part of simulation structure. The definitions dependent on metric category for in-crash simulation structures are as just stated here on the left-hand side. So for example, what are those metrics? We call them safety criticality and crash parameters, which do not very much involve injury assessments already, but define something like an avoidance rate based on time to collision, post-encroachment time, whatever. This is not really in crash simulation. So it's really about pre-crash metrics. If there is, for example, no avoidance possible, then we can talk about collision velocity, impact velocity, if there happened a collision, and we can create a metric on how many collisions maybe happened or not. There is a possibility to continue with injury risk functions afterwards. So for example, based on collision velocities, we can assess, can create injury risk functions, but there's also, of course, more complex metrics available. For example, the in-crash kinematics, for this we need to perform then vehicle structure crash simulation, from which we can then have outputs in terms of mechanical damages, delta V, crash pulses, so an acceleration time signal, energy equivalent speeds, also a criteria has been developed in our community over the last years. We can talk about VAU injury assessment. Of course, we can as well perform here simulations with a vehicle structure from a car. We can we need to simulate maybe the occupant or the opponent, the human. It can be a cyclist, a pedestrian. And from here, we can really go into the personal injury level, for example, with a head injury criterion, brain injury criterion, or neck damage criteria. And finally, we talk about occupant injury assessment. So we have a vehicle structure. It's in a way the most complex because you need multiple simulation domains as well. The vehicle structure, a restraint system, for example, airbag, seat belts, and the occupant inside this kind of system, where you then assess finally as well personal injuries, for example, hit, brick, and NIJs. Coming back to the overview, what is then the last step? We can talk about optional information, for example, weather, lighting conditions, which are used to perform the simulation. What can be some designed and optional elements based on the scenario, for example, the opponent can be included. So is it a single vehicle crash or is there some other participants involved? Then you need to model as well the opponent. When you talk about environmental conditions, do you want to change the weather? Should there be some friction, different kind of friction values based on rain? Should there be day and night situations? Of course, you always need to simulate such things as well with your finally maybe sensor models. And finally, as Sitze already said, we also are talking about behavior models. So if you want to include, for example, human models, behavioral models into the simulation, this can be as well done to really assess the implications of such models to the different accident. Yeah. And finally, when you have then performed the 3 steps, you get your final simulation structure, and you know which kind of models, for which kind of models, you need to define the modeling approaches. So let's take an example here, define simulation structure. Let's assume we have a research question defined. What is the safety performance of a speed bump in a car to cyclist crossing situation at changing lighting conditions day and night in an urban environment in terms of impact velocity reduction? Quite complex, but we always try to put everything we need to assess in this kind of research question. So we start with a simulation structure. So we have a speed bump, which relates to an infrastructure-related pre-crash measure in the cluster number 3. And then we also have a cyclist. So it fits. We have the cluster number 3, and the cluster number 3 very basically defines as well the modeled, the models you need to have at hand. So this is here, cluster number 3, infra-related pre-crash measures. You need to have mechanics models for the traffic and the opponent. You need to have, and here's also the safety technology related infrastructure measures, which you then change via your assessment. So you choose the cluster number 3. It's a pre-crash related safety measure. So you choose what kind of metric you want to have. In this case, it's in a way safety criticality and crash parameters. It's the impact velocity reduction measure we want to perform. Basically this, what you just saw. And then you refine the simulation structure based on additional scenario information. So as we have seen, we want to also change the lighting conditions. So we need to include weather and lighting conditions as well, which are here down there. So of course, we need to have a model for the lighting conditions in our simulation. And when you have walked through the 3 steps of our, let's say, method, then you have your full simulation structure at hand. And you can use this simulation structure to choose then afterwards the right models. And this is where I come into play. So select modeling approaches for previous elements. I don't know, is there questions already, Sitze, or?
Yes, I wanted to check with the audience. Are there any questions at this stage? And you can enter them in the Q&A part. So let's see whether you have questions.
Okay.
I have one question for you. Lars, you showed in the pre-crash at the top left, you showed both mechanics and technology. So what in a way there can be also a technological solution in the mechanics. So what is the difference between these 2 blocks in the simulation structure?
So normally, you're right, of course, maybe there can be some technology in mechanics, but when we talk about technology, we mean the logic part. So in a way, a function, an A/B function, it can be a sensor, something like this in that direction. So it's really a a good question. It's a technology adding to the vehicle from a functional point of view.
Yeah. And the mechanics part is mostly then the vehicle dynamics and
exactly.
those kind of,
yeah, you will see it later. You will see it later that we have another slide going a little more down the line, and the mechanics part, you're right, is the dynamics and also the geometry from that car or from that traffic participant. Yeah.
Okay, thanks. I see no new questions, so let's continue with the slides.
Thanks. Yeah, okay. Select modeling approaches for pre-crash elements. So we have divided the presentation into 2 parts. Pre-crash elements, it's really about the situation before the crash happens, and then the in-crash elements, really going into finite element injury risk assessments and so on. So what it's about, let's assume we have the cluster at hand. How to continue here, really choosing the right models for the different elements we have chosen. Yeah, for example, we know now we need a mechanics part to perform the simulation. What kind of mechanics or then dynamics models are available to us and which shall be used. So in the project, we went through the different elements and have put all the knowledge together to define models which can be used. We also have defined for people starting in that direction how to select models and what are also dependencies between different kind of models. The idea of going from simple to complex, quite easy to understand, but how to very generally talk about modeling approaches. And finally, I want to talk about a little about the open source models. So in the V4SAFETY, we have developed 3 different, is it then technology models? You see it. So different models which can be used to perform assessments, which hopefully gives an easier start to do such performance analysis, which we want to share to the group as well. Okay, finally, you see the different clusters on the one hand, but as well our distinguishing between the models. So we start, in our view, with a world model. Then we have the 3 different main parts, the infrastructure, the traffic, and the environment. And we also did not redefine the wheel. So when you talk about infrastructure, traffic, environment, you see as well the relation to the so-called Pegasus model, which we are as well seeing here. So we have inside the infrastructure, we have different kind of layers from a Pegasus perspective, road signs, and temporal modifications, and we define different kind of modeling approaches for infrastructure. In dark green, you see them, and we have a list of modeling approaches which we provide for the dark green bubbles in this overview. And all the light green bubbles are in a way included as well, of course, into those questions. For the traffic, it's divided in different parts. As we just stated, we have the human, we have the technology, for example, sensors, functions as well. And we also have the mechanics, which we basically divide into geometry data and dynamics data. We have the human, from the cluster you saw it, the human controller, which defines then the traffic participant. We try to make it as generic as possible because the traffic can be a cyclist, it can be a pedestrian, it can be a car driver, whatever. So all those vulnerable road users or infrastructure users can be defined with this kind of elements. And then finally, we have the surrounding and the environment and the digital information, which is, of course, as well needed to perform simulations. And for here as well, we have defined some questions which can be followed. Just before stepping into the process itself, talking about the models from simple to complex. You later see questions in the relation of mechanics, but of course, when we talk about sensor models, this is as well something we have to have in mind. And generally speaking, depending on stage of technology development or technology assessment, different model abstractions are possible. Yeah, so when you want to assess, for example, an A/B function very generically, you do not think about sensor functionalities at first. So you maybe idealize your sensors in an ideal ground truth manner, or you maybe increase the quality with some stochastic elements. But if you want to perform validation of your system, you also need to definitely simulate with a stochastic sensor, because you cannot abstract all the sensor-specific elements, and you cannot neglect those for the safety performance assessment later. If you, for example, want to assess or validate the function of a specific sensor and the implications to safety performance, you need to model those sensors in depth, and you maybe need some physics-based sensors as well. So simple models for initial and early assessments would be our proposal. Start with that. From a wider viewpoint, if we want to talk about validation, we need to include as well complex models, but of course a simulation then increases in complexity as well, which we sometimes do not want to do. And of course, you need to have more complex models when your technology lies there where you want to assess it. And very generally speaking, the effort you need to do to create, verify, and validate single models can increase very fast. Okay. The pre-cache modeling approaches, how to go there. So we start again with the evaluation scope, the model requirements, and then we have the different modeling approaches. So in our deliverable and as well in the processor, which has not been shown today, you see the different kind of modeling approaches we propose. For example, for the mechanics, the dynamics element, we have very, very simple models like position over time, point pass models, single two-track models, but later as well, maybe multi-body or machine learning models. Everyone has a requirement, a capability, a limitation, input, output, and also examples. And this is what we provide for each element, for example, here the mechanics part. And based on this modeling approaches, we want to select the suitable modeling approach. And we also have here defined questions. So, for example, we say what is the model input, what is a model property, the model output. And for each of those models, we provide answers to, is the model can it consider any actuation, or does it need to consider any actuation input? If there is a yes, then different kind of models cannot be used anymore. So we start from the minimal part. So all these answers are maybe no. Then you can start with a very simple model. But if there is yeses, then the complexity and the advancement of the models increase, which you then have to use. And this we provide for all the different elements in that structure. And you go through those questions, and finally you come to the answer, what kind of models you want to have. All this can be found in the deliverable, but also in the V4SAFETY processor. And you already see maybe why we decided to create a V4SAFETY processor, because answering such Excel tables is quite time consuming, and the processor provides us with a good way to have a clickable solution and find the right models for the simulation. The second part of the pre-cache modeling approach is the interconnection, the model dependencies. So if there's, for example, a dependency between the mechanics part of the ego, the opponent, or the infrastructure. We as well have some questions. And you see here, for example, if there is, for example, an infrastructure model needed, or is a specific type of infrastructure model, then this also applies. We need to have different kind of models from a mechanics point of view to perform such simulations. And then we exclude different kind of modeling approaches from that interconnection to other elements. Yeah, same there, going through all the interdependencies, and finally we have a process and approaches which at least have to be used to perform the simulation. I stated it already, we have a V4Safety open source models. We shared it via the OFTO Git. So everyone, is invited to take a look. We have 3 different models, an A/B technology model, in forward collision warning model, and also in I2V, so infrastructure to vehicle model, being created by the different partners of the V4Safety consortium. For the A/B technology, for example, what is included? So there's a generic object sensor model inside. There's a collision prediction module, a TTC calculation module, and also a brake module. And finally, just to show you what you can do with that, we also used it in the different use cases in V4Safety. We can perform an assessment of, let's say, one scenario, baseline scenario here in this case, an accident between a car and a cyclist. And by applying this kind of technology model, we are able, you saw it, to stop that accident, and we can then compare later on and summarize how many accidents could have been avoided by such a technology. So our vehicle was then able to stop and detect the pedestrian, or the cyclist in this case, sorry, early enough. And this is an easy start to start with safety performance assessments. Continuing with the in-crash elements, I think it's quite a short one, but it's also very necessary. So we are not just considering accidents avoided or not, but really talk about how, what kind of models are existing. It's a lot, and just to name it, what was the history? We started with a huge inventory of different kind of in-crash simulation approaches for road, furniture, vehicle structures, restraint systems, occupants, but also injury risks. And we as well created an in-crash simulation overview with a table, as well requirements, solver types, capabilities, limitations, and also examples we have seen over the last year in the community being used. What is the starting point for this in-crash modeling approaches? It's always it starts as well here from the evaluation scope. We have a systematic walkthrough of in-crash simulation structure, fulfilling all requirements and dependencies. And maybe one example to show it here, if someone would have chosen a metric number of fractured ribs on a stress strain based metric, so it's really the details of a human in a way. The road user type is the vehicle occupant, and the safety measure would be an in-vehicle pre-crash related measure, maybe an A/B technology. So we start then with the approach with a number of fractured ribs. So how can we assess that? There's 2 options. We have an finite element occupant human body model, or a finite element vulnerable road user human body model. So as I stated, fracture ribs, we know we have to use human body models for that assessment, and to have an occupant human body model at hand, we need to have different kind of inputs. Yeah, so of course we need to have a vehicle model at hand. For that vehicle model, we need to have a restraint system. We maybe need a road model as well, so that model drives on. And we also need to have a road furniture model, like an opponent to which this model is being crashed to. This is one example, so really going with a complete full vehicle model simulation. The other option could be that we just have a finite element vehicle interior model. Yeah, so this is a reduction, really concentrating on the relevant elements of a vehicle. This model then needs a so-called crash pulse, so an acceleration over time signal, which has been used for the simulation. And we need to have the finite element restraint system to assess occupant injuries. The crash pulse can be gathered, of course, via different kind of models as well. So the vehicle structure model, again, the vehicle model, the road model, and the opponent model, but it doesn't have to be a finite element model. It can also be multi-body models, for example, which I then use to assess the crash pulse. So quite complex. You have to dig into the material, but from the process, everything is in a way quite good documented how to come to the right models you need to in-crash simulate him. And finally, of course, there's a different ways you can go for to assess the number of fractured ribs based on the different models you maybe have, you maybe not have. You need to idealize, you need to abstract, whatever. Model interfaces, of course, a very important part. So you need to connect models with different kind of tools, maybe. So interfaces are something which is quite relevant as well for the so-called ASAM community. We have static file-based interfaces defined, and we reference, very basically to open drives, open scenarios, open CRG files. We also documented in our deliverable quite good that you have a good start for such things. We have dynamic elements, which are, for example, the open simulation interfaces to really how, in a closed loop manner, how to provide data signals from one to the other. There's also, OSI, but also the FMI Modelica functional model interfaces, which are at least in Germany quite a lot been used. And finally, we have simulation tools and supported interfaces. So when you really want to start with a framework, you can use, for example, Kala, P.E.A.R.S as well. Volvo developed the ES Mini, quite very good. Zumo, Omnet for communication simulation. Yeah, and normally we would then start or go to the V4SAFETY processor. This is what we will not do. So maybe you can say it, but we decided that Peter should document or have maybe Pizitza, you take over here.
If you click once more, I added one screen. Oh, it's a different. Okay. The V4SAFETY processor essentially helps you to go through all these steps that Lars presented, but then in a software-supported tool. So you make your selections, and it will pop up the appropriate tables and appropriate views automatically. So that makes it a lot more easy to use, and takes less reading as well. And it's also a way to check, even if you already have a simulation structure and available, to check, did we see any difference? Is there something, an optional element that we have in but may actually be left out? Or is there a recommended model that we do not have in ourselves, or that might be an alternative? So it's a quick way of going through all the the logic that's captured in what Lars presented. And it also hopefully helps to make simulation structures more comparable, simply because you show them in the same way, but also because you use a unified process to get to a simulation structure.
Yep. And I think we decided that we will document the usage of the V4Safety processor in a screen recording, and we will share it as well afterwards. Yeah, so yes. Everyone who's looking forward to that is invited to take a look at that as well. Yeah.
Yeah. So that's on the processor. And this might be a good, there's questions in the Q&A. So Lars, can you see them? I will pick them out.
Okay. Yeah,
please read out the question as well.
Okay.
So the first one is on can this simulation framework be used if you have more than 2 object types? So we typically have one vehicle and one other road users. And can it also be used for, say, 2 cyclists, or a cyclist and an e-scooter and a car?
Yeah, I think this is a question which is covered a lot. So you just see the framework from, let's say, traffic and another traffic opponent. But I guess in the V4Safety processor, we also have included it. So of course, you can just add different kind of traffic participants into your structure, and it just adds up. So yes, it's possible. It's quite generic. Normally, you just start with an assessment of just 2 participants. But when, for example, the truck has side obstruction or whatever, yes, you can do that.
Okay, thank you. Then there's a comment on the open source models. So they are published at OFTO, the Open VT organization. And there's a web link there. I'm going to copy and also put it in the chat just to make sure that everybody has it.
Yeah, thanks, Sitze.
The chat is turned off. Okay. So that one, we will make sure that we add it to the website, and so that you can find it. Good. Then
you can see it, Sitze. This Q&A is the chat. Everybody can see it.
Can see it. Very good.
One question from Kong Xiaolin. How to cluster the simulation based on the objects to be protected, especially with a motorcycle? Does it based on size or space? I don't know if I understand the question correctly.
Okay. So Lynn, maybe you can add a bit to your question.
On the one hand, or you can also maybe just directly contact, if you like, via LinkedIn, Xiaolin, then we can have a short discussion if you like, just a proposal. Yeah.
Yeah. Okay. So this might be on the geometry of the motorcycle. Is it a bounding box that you use, or are we talking about real geometry of handlebars, a seat, etc., an engine? So how is that handled?
It depends then finally, of course, on the safety measure you want to perform. So if you want to assess, for example, a motorcycle driver, as human, you have to model as well the motorcycle from the one hand. But this is the in-crash related measures where you need to model a lot. From the pre-crash point of view, you can, of course, have a different way of modeling. So depending on your defined sensor set, for example, it can be a bounding box. So it doesn't have to be connected. Yeah.
Okay. And then there is a question from Robert Demkes. does the processor produce open scenario and open road models or open drive? No.
No, the processor is basically just defining setting up. To have the models, the right models at hand, Robert. It's not about really creating those. Yeah, we have not developed such thing because there's some already available open source, but this is not what we have done in the project.
So what the processor outputs you can store as an SSD file. So that's a simulation structure file, which some of the simulation environments can read. And you can also export it as an SVG file, but that's simply an image that you can then use in your reporting or documentation. So as a final thing, I would like to point to the deliverable that has become available online today. And this is D5.1. I put a link to the outputs folder in the chat. That's where you can find all the V4SAFETY results, and it includes the report on simulation structure as well. And on the same page, we will also publish the direct link to the processor. So it will become available online for you to use yourself, running from a server at a virtual vehicle. So you can try it yourself and use it yourself there. This is expected within 2 weeks. So just to summarize, all the documentation in the D5.1 report on simulation structure is there. Good. Are there any other questions? Then we will. Thank you. Then we will keep open the webinar for 2 more minutes, just to if there are any late questions popping up. So you will be receiving a link to the recording of the processor once it's available. And we thank you very much for attending. And if there are any questions later, please just send a message to the organization. And thanks for the hands. And a special thanks for Lars for taking over Peter Riemer's role. Yeah.